Hello, welcome, Isaac with his traditional Ola nerds. It's Friday, right? Good day. Good morning, Maggie. Um, Hello, Naya. So, Naya, let me know if stream's less laggy today because I lowered it down to 720p instead of 1080, and I lowered the bitrate a little bit, so it should be smoother for everybody. Hopefully, a little less laggy, less buffering is the hope. Although it will be slightly less crisp, but if as long as you're okay with it, that thanks, Naya. Yeah, it should be better. I didn't realize that if you're not a Twitch partner, it doesn't. You don't get your viewers don't get the option of changing the resolution. Um, so it's whatever I stream at is what you guys get it at. So learned that on Wednesday, and now I lowered it down to 720p. So learning all the things about streaming. You guys think you're the only ones who has to learn. Oh man, I feel so bad for teachers that don't know how technology works. I have no idea what they're doing. Oh, let's see. How is everybody? How are we doing? We doing all right? We holding in there? The Witcher. Oh, really? Interesting. Yeah. Some people were saying the show is pretty good. But yeah, elementary was somebody playing these weird learning games. I'm sorry, Maggie. So my son has some preschool stuff, but his teacher just like uploaded a couple like 5 minute clips, and they have a packet they're supposed to work through, but it's preschool, so um, yeah, I've never gotten into the Witcher series, Naya. It's not something I've ever played or gotten into. I guess I could see since you're really into Skyrim, right? It's a similar genre ish. Well, that's cool. Something to do. Always got you. Got to find something to do. You got to stay busy. Yeah, gotta play. Gotta stay busy. Gotta stay busy. I like I said, so I looking at the numbers and the predictions and the models and things. I wouldn't be surprised if they kept quarantine in effect until like June 1st. But I think in June they're gonna go. I'm fine, Isaac, but I also like most of my friends are online anyway. Um, I play video games in my free time, and so like being stuck in my house is totally fine with me. Um, that's where I get most of my social interaction anyway. It is kind of rough that I don't get to hang out with like my extended family because we usually get together with them, once a month or once or twice a month. Um, so that's a little rough not getting to hang out with them. And then my wife is having a hard time, and so since she's having a hard time, it makes it hard on me sometimes because our kids are crazy. I think having the kids are my young children are the hardest thing to do. Yeah, I think, like I said, I think they're gonna relax a lot of the quarantine and stay at home orders and all those things on June 1st would be that's my prediction. Again, that's totally me. That's nothing official, but based on like the models and the things I've looked at, that's going to be the one of the more likely cases. So, um, well, Naya, you're at an age. 18 is kind of the age that you really want to get away from parents. Um, that's just the age. There's a reason why the college is there. So we'll see, Lauren. We'll see. There's some interesting stirrings among some like private business owners that are getting like fed up with running out of money, and that might start pressuring the governor to reopen stuff earlier. But we'll see what happens. My bet is in June. So most of the models are predicting like peak resource usage and peak COVID-19 cases around May 1st or 2nd, which means after another month of that, then we'll probably be in a state that we can allow social gatherings and things again. Well, so I mean, what they might end up doing, because democracies are interesting. So there's going to be potential like protest. People might just open to be belligerent. There's going to be some interesting things. Lauren, I actually need to ask you guys that question right now, right? Um, that's hilarious, Naya. Um, Micah, your family's so weird, and I love it. Okay, anyway, so Lauren's question, what are we going to do after the AP test? That's a great question, because our AP test, the chemistry test, is the first week of testing. It's on Thursday, which I know most of you have multiple AP tests, and so most of you are going to have some other tests you're going to have to study for. So my question to you guys, there's a couple options of what we can do. I haven't decided anything officially yet. So after the AP test, we can either do a little like miniature unit on organic chemistry, which I think is some pretty interesting, pretty cool stuff. We could have just like one homework assignment on it, and that would be it. So yeah, we could do organic, or we could do some semblance of an independent project where you guys kind of try to do some something at home where you like make your own little YouTube videos, and we do like we have like a day where we watch a bunch of your videos on stream, which would be kind of cool. So those are kind of the two options I'm toying with. Either just teaching OChem and doing OChem and having an OChem assignment, or having you guys do some semblance of an independent project as much as you can at home, and then we would just kind of watch everyone's videos as a class. So basically OChem or project are the two things. I'll make a poll for that, and I'll send out a poll for you guys to do over the weekend. So that's the thing, Maggie. We'll see. I'll send out a poll. I'll see what everybody says. Those are kind of the two thoughts right now. So I'll put a survey up on Canvas. I'll put a link to it. I'll do that this afternoon, and then I'll finalize the calendar next week and send that out to you guys. So I have everything up until the test planned, but we have one more week of class after the test. So I'll send out a survey. You guys can answer the survey, put your votes there, and we'll just kind of see what everybody says, and we'll go with the majority. And that's not to say that if you want to do your own little project, you can't. Maybe we'll do that as like an extra credit or something. Yeah. So Lauren, because the AP tests are pushed back a week, we only have 2 weeks of school, but that last week of school doesn't actually matter. And so we really only have a week after the test, because the test is on May 14th, and so we only have that week of the 18th to the 22nd of more instruction, and then Memorial Day is on the 25th, and graduation's on the 27th. So because the test got pushed back, we really only have a week. So Maggie, because graduation's on Wednesday, most teachers are going to have grades finalized by Friday the 24th of May. That's April. Friday the 22nd of May. They are so not a physical graduation, Isaac, but they're looking into a bunch of like digital alternatives for graduation. The principals I know were having all the principals in the district were having a meeting today, they were going to have a meeting today to decide what they were going to do for graduation. So you'll potentially see some info about graduation next week. Oh my gosh, Bryce, I do not know, because they dropped another bomb on us that we have to like move out of our classrooms because they're going to demolish them. So I'm going to try to do stuff at some point. I don't have BYU anymore. BYU's done. Micah, to be completely honest, if you're doing everything, you're going to end up with an A. So, yeah. As long as you're doing everything, your grade will be fine. A or A minus is going to be the bet. So just keep up and do everything and you'll be fine. Because my focus is that you guys pass the AP test, right? I know that this quarantine situation is crazy. So for me, if you're doing it, Lauren, you'll be fine. You can get a 3, I believe. How are you counting late assignments? I'm not. I'm just giving you credit as long as you get them in. So just get them in. Get them in, get them in, get them in. Okay, that's enough like introduction stuff. Let me know. I haven't checked to see. Like I said, I'm gonna try to get grades updated into Skyward this weekend. I think that's a reasonable goal. I'm gonna make myself do it so I don't procrastinate. Isaac, you're gonna get a 5. Come on, you can get a 5. Okay. Let's get into the review. So, I guess not the review, the 2016. So, I went ahead and added up the total points. If we skip number 3, E and F, there are 43 total points on the short answer. And so, if you got more than 34 of those 43, that's a 5. If you got 28 or more, that's a 4. If you got 22 or more, that's a 3. So, hopefully you guys added up your scores after you graded yourself and you got that turned in last night. If not, try to get it turned in. If you got exactly 34, I don't know how that would round, Isaac. I think that's a 5, but just barely. So Naya, they're gonna do 2 long short answers. That's what they've said. It's gonna be 2 long. So it'll basically be like numbers 1 and 2. And they're going to try to word them so that they cover a broader range. 5's the highest score you can get, CAPSEP, on AP tests. So 5's the best score. I think it's open note, Maggie. That's what I saw on the College Board website. I'm going to look more. They're updating it almost daily. I think he's just another random person joining in, Isaac. Yeah, so definitely it is open note. That's what they've said. Oh, from Germany. Cool, Germany. So yeah, the advanced placement test is for high school students to get college credit. And so this is a high school class, but it's being taught at the collegiate level for, intro to general chemistry. Okay, Micah wants to do every question. What questions do you guys want to do? Yeah, Naya, maybe I'll do that. Maybe the day before the test, we'll do some cool stuff. All right, 2E and 5C. Oh gosh, okay, so let's get into it. So let's go to E. That was the first one. Haley was first. 2E. So this is a Lewis structure question. Okay, so it says the bicarbonate ion. You guys, remember the chapter that we did, Lewis structures? This question was on that test. I literally copied and pasted this question onto that test. Okay, so we're drawing the Lewis structure for the bicarbonate ion. Okay, so let's get rid of this. Okay, so we have the bicarbonate, HCO3 minus. The problem says it has 3 carbon-oxygen bonds. So our carbon's in the middle and our oxygens are all around the outside. DJ made the same mistake. You're supposed to learn from your mistakes. The hydrogen atom is bonded to one of the oxygens. Okay, so basically what they're saying is they're saying that we have this Lewis structure. Yeah, resonance. Good. Maggie remembered resonance. So remember, if we draw the Lewis structure here, we end up with like something that should look like this. Right? And then remembering that there's resonance between the oxygens. And so we have these two Lewis structures, right? Okay. So we have resonance. So technically these bonds here, this CO and that CO, those are the same length because there's resonance. Whenever you have resonance, instead of thinking of this as a double bond and a single bond, we can think of it as a 1.5 bond, right? So 1.5 here, 1.5 there, 1.5 here, 1.5 there, right? Let's see. Hold on. Questions. Okay, I did it. It was like the problem says one OC is longer than the other two. So a double bond does make it shorter. Okay, so these two bonds here are shorter because they are 1.5 bonds. This bond here is longer because it is a single bond. Right? So remember, resonance makes these bonds stronger and shorter. This bond is going to be weaker and longer because you can't have resonance to this oxygen because it's busy bonding with the hydrogen. Okay. Isn't a double shorter than a single? Yeah. So a double shorter than a single. But remember, there's resonance. There's resonance. This isn't a double and this isn't a single. These are both 1.5 because of resonance. So for the points on this one, if we look at the grading key on this one, 2E, so you needed to have the structure drawn. They drew it kind of like this. You got points for the correct Lewis structure, right? So one of the correct Lewis structures got a point. And then you got a point for indicating resonance. So you had to show resonance in order to get both points. Yeah, no, Micah, the electron does not go back and forth. So let's see. Lauren had a question about D. In thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering the flask gets cooler as the reaction proceeds, what drives a chemical reaction? Okay, so before I do this, let me answer Naya's question real quick. Resonance is whenever you have a double bond that could be drawn on multiple locations. So when we draw, say we drew this structure first. When we draw this structure and we get to the point that we're like, oh, well, we need a double bond. Do we put a double bond here or here? And the answer is yes. The double bond is on both. So whenever you have a question of, oh, I could put a double bond here or here, and that would be the same, then it's on both. Or in some cases, it can be on all three, like in the nitrate ion. Okay, so back to Lauren's question about part E. Okay, so if it gets cooler, so remember, this technically won't be on the test because I think this is from unit 8 or 9. But we talked about it, so might as well go through it. We have the equation for spontaneity. Delta G equals delta H minus T delta S. So remember, in order for a reaction to be spontaneous, delta G has to be negative. If the reaction is endothermic, aka it gets colder endothermic, delta H is positive. So if this number is positive, the only way to make this number negative is if this number is positive. Right? So if the reaction is endothermic, delta S must be positive. So that's kind of what the problem is getting at here. It's saying what drives a chemical reaction? It's going to be the entropy. The entropy is what drives the reaction. Justify in terms of delta G. Yep. Will there not be a question like 1A? 1A. No, there will be 1A because that's delta H. Sorry, Billie Jean. I have no idea how to synthesize that compound. I'm not a synthetic organic chemist. So yes, there definitely will be a problem like 1A. This is a delta H calculation. This is a Q equals MC delta T. So this one's fine. But things like enthalpy, the first chapter we did on thermodynamics will be on the test, but the second chapter we did on thermochem will not be on the test. So like delta S and delta G won't be on the shortened AP test. Okay, let's see. Next question. So let's do 6 and 7. People asked about 6 and 7. Since we're on one, lattice enthalpy is positive, indicates the energy to break it apart. However, the dissolution is an exothermic process. Identify all the particle-particle interactions. Oh, so this is that idea of a dipole, a ion dipole force. So if we're going to dissolve lithium chloride, we break the ionic bonds, but we form ion dipole forces. And those ion dipole forces are what makes it exothermic. I think that's probably what the answer key says. Question 2, 1F. Ions are polar, water molecule polar, so ion dipole interactions, yeah. While we're here, 1E below's representation. Oh, okay. So remember when you form an ion, positive ions are smaller and negative ions are larger. And so since this guy is big, it's going to be the chloride ion. And since this guy is small, it's going to be the lithium ion. So whenever you make a cation, a positive ion, it shrinks. Whenever you make an anion, a negative ion, it gets larger. If you didn't say ion dipole, we said dipole between the ion. Would you get the point? Yeah, if you said it was between the ion and the water molecules, you would probably get the point, Sammy. But to be sure, or to be safe, whenever you're talking about an ionic compound dissolving, it's forming ion dipole forces. So, Micah, it does have to do with the radius of the atoms, but remember when we take away or add electrons, the ions change. So a positive ion is always going to be smaller, a negative ion is always going to be larger. So it's both the atoms and the ions. But yeah, so I want to say, see the diagram above, 1 point is indicated for correct identifications. So, yeah. Okay, so 6 and 7. Let's go to 6 and 7. Sorry, I'm doing this really fast. It's kind of a whirlwind. I hope you guys are getting your questions answered. Okay, question 5. Question 6. Okay. The polyatomic ion, that grossness, because organic synthesization is a difficult thing to do, Billie Jean? Okay, so the polyatomic ion C10H12 into O4 into A4 minus, commonly abbreviated as EDTA, 4 negative. The ion can form complexes with metal ions in solution. They gave us the K here. A complex with barium forms according to the equation. So let's see. So right now we know that K is very large, 10 to the positive 7th. So we know this reaction is very forward directioned. Okay, a 50 milliliter volume solution of EDTA has a concentration of 0.3 molar. It's mixed with 50 milliliters of 0.2 molar to produce a 100 milliliter solution. Considering the value of K for the reaction, determine the concentration of BA EDTA in the 100 milliliter solution. Justify your answer. Okay, so because K is very large, we can assume the reaction goes to completion. So let me jot down a few things and then we'll switch over to my notepad. (7.7 times 10 to the 7th). So we used 50 milliliters of 0.2 molar and 50 milliliters of 0.3 molar. Okay, cool. All right. So let's go to my work here. All right. So this is the thing they gave us. They said 50 milliliters of 0.2, 50 milliliters of 0.3, and we want to know how much of this is produced. So what we can do is, because K is so large, we can do a Bicarbonate table, right? I mean, that's what Bicarbonate was used for, is when we did reactions that had very large Ks, so why not just use a Bicarbonate? So 50 milliliters of 0.2 molar, that's what, like, if we multiply these together to get the molar, or the number of moles, divide by 1,000. I need a calculator. Calculator. 50 times 0.2. So this is 10 divided by 1,000. 0.01. So we have 0.010 moles of this. We do the same thing here. This would be what, like 15 divided by 1,000. So we get 0.015 moles. Start with 0. Yeah, no, Bicarbonate works. All right, so minus 0.01 minus 0.01 plus 0.01, 0. 0.005 moles, 0.010 moles, right? Divided by the total volume, 0.1 liters, gives me 0.1 molar. Let's see if that, sorry. Whoop. Let's see if that's what the answer key says. So answer key says, based on the K value, the reaction goes to completion. Barium's the limiting reactant, 0.1, 0.1. So 1 point is indicating the equilibrium concentration is the same as the original concentration of barium. 1 point, yeah, okay. You could synthesize sodium chloride, but why? All you have to do is take salt water, or like ocean water, and evaporate it. Why to divide by the total volume, Lauren? Because a Bicarbonate table always gives you moles, and the question asked for molarity, right? And in the end, right, you're mixing the two solutions together, so you need to divide by the total volume. Okay. Hopefully that helps. All right, let's go to part B of the problem. Part B asks, the solution is diluted with water to a total volume of 1 liter. After equilibrium has been re-established, is the number of moles of barium present in the solution greater than, less than, or equal to the number of moles of barium present in the original solution before it was diluted? Justify your answer. Okay. Let's see. There's a couple ways you could approach this problem. You could do it from like a Le Chatelier's principle standpoint, because if we think about this reaction, so Bicarbonate is when for reactions go to completion, Naya, because that lets us do like a limiting reactant idea. Ice is when you have something at equilibrium. Basically, a Bicarbonate is like a simplification of an ice table for reactions that go to completion. You could have done this problem with an ice table. It's just a whole lot harder to solve. Because your K is so large. Okay. So like I said, so for this problem, there's a couple of, you do Le Chatelier's principle. So if we think about Le Chatelier's principle, if we add water to this reaction, we're diluting both the left side and the right side, but we're diluting the left side more because there's more substances on the left. And so Le Chatelier's principle is going to shift this reaction to the left, because it's getting diluted more. And so the barium ion concentration, the number of moles, would actually go up because the reaction would shift to the left by diluting it. So that's the simplest explanation, is just to use Le Chatelier's principle. You could actually do an ice table and show that it's going to shift to the left. But I wonder, what did they say? Okay, I knew they had a couple. Okay, so the number of increases because the percentage associated increases associated diluted. That's the Le Chatelier's example. And then they say a mathematical justification. Oh, so they just basically mathematically justify, hey, where Q is greater, or Q is less than K, or sorry, Q is greater than K, so then it will shift to the left. So they did like a Q versus K calculation as well. So yeah, either Le Chatelier's principle or actually plugging in and using a Q is greater than K. Zach, to answer your question, how big should K be for a Bacot table? I would say anything greater than like 10 to the 4th power is probably big enough. Okay, so that's problem number 6. Yeah, oh yeah, 10,000. I mean, this one's 10 to the 7th, right? That's 77 million. All right. Number 7. Ooh, number 7's a good one. I'm pretty sure I put this one on one of your tests that we did earlier in the year as well. So, a student is given 25 milliliter sample of an unknown monoprotic acid. Yeah, Isaac remembers it was on the Chapter 4 test. I knew it was. Why would you want to synthesize creatine at home? Just buy it. There are literal massive companies and factories that make this stuff for you. It will not be cheaper. There's no way that you have the setup to do it at home. You can find creatine in bulk for super cheap. And plus, without being an actual like certified synthetic chemist, you're asking for trouble by trying to synthesize your own chemicals. All right, so 25 milliliter sample of an unknown monoprotic acid has to determine the concentration. Not for creatine, you wouldn't be. Yeah, sorry, you're not Jesse from Breaking Bad. Creatine is just a supplement people can do. Maybe, Haley. We should have enough time. Okay, so onto the problem. The student standardized a solution using 0.10110 molar sodium hydroxide, burette, a flask, appropriate indicator, and other laboratory necessary equipment. The image shows the burette before the titration begins below the left and the endpoint below the right. What should the student record as the volume? Okay, so let's zoom in a little bit. And by a little bit, I mean a lot. Okay, so if we look at this one, we've got, this is 5, 5.5, 5.6, 5.7. So it's in between 5.6 and 5.7. So because it's in between 5.6 and 5.7, we would say, what, 5.65 as our initial volume? You could maybe make a case for it being 5.66, but I would say somewhere around 5.65, 5.66. And then if we go to the final volume, this looks like 37, 37.1, 0.2. It's pretty much dead on the 37.3 line, maybe 37.31, but definitely 37.3 something. 3.0, I'll go with 3.1. That meniscus looks like it's below the line there. But 3.031 with sig figs, remember that last digit can vary slightly, right? So let's zoom back out. All we got to do is then find the volume, right? So we just subtract the two. So 37.31 minus 5.65. Milliliters. So I get 31.66. Okay. So if we, again, to show the work on that, right? 2 places pass. No, so you want to make sure you have proper sig figs. So if we look at the answer key on this one, the answer key says 31.65. 1 point is earned for the correct volume. So I assume that they probably were only awarding this point if you use the proper sig figs. So good. Tell your small motors teacher that you were doing it right. All right. So you have to. I would argue that if someone put 31.6, they probably would not have given them the point on this one, because this is a reading glassware question, and so you have to make sure you understand that you're reading glassware properly. So, okay, back to the question. Part B then asks, based on the given information in your answer to Part A, determine the value of the concentration of the acid that should be recorded. Now, no matter what you put for Part A, if you use it properly in Part B, you'll get the point. Okay, so they told us that it was 25 milliliters of acid. We just found that we used 31.66 milliliters of sodium hydroxide. They told us the concentration of the sodium hydroxide is 0.1100, molarity. Okay, so the simplest way to do this, because this is a 1-to-1 titration, the simplest way is to do just M1V1. So we can say M1V1 equals M2V2, and we can solve, or you could do a factor label. Either one will work. So we're trying to find the molarity of the acid, right? 25 milliliters equals 0.110 molar times 31.66 milliliters. Multiply, divide, you find the molarity of the acid. I'll show you how to, I'll show the factor label too. Let me calculate this. 31.66 times 0.110 divided by 25. I get 0.139 molar. Okay, now how to do a factor label. How many moles of HA are in 1 liter of solution? 1 liter is 1,000 milliliters. 25 milliliters of HA required 31.66 milliliters of NaOH. 1,000 milliliters of the NaOH solution contains 0.110 moles of NaOH. And then the last step, you would want to say 1 mole of NaOH reacts with 1 mole of HA. Okay, good. Oh, that's good, Naya, that if you just got your first buffer, that means that it's doing a lot better. All right, so the answer key on this one, answer key says 0.139 molar is the answer. Because HA is monoprotic, so they show kind of they use an M1V1 here in the OR, so you can do it that way. I think the prompt says it's monoprotic, doesn't it? Does the prompt say monoprotic? The prompt says, yeah, an unknown monoprotic acid. So that was the giveaway for the 1-to-1 ratio, Anna. If it says monoprotic, that means it has 1 acidic hydrogen. If it had been a diprotic acid, you would have to do like you would have to do a factor label, and in your factor label you'd have to do that 2-to-1 molar ratio idea. Okay, so 1 point here, and then part C asks, in a second trial, a student accidentally added more sodium hydroxide to the flask than was needed to reach the endpoint, then recorded the final volume. Would this error increase, decrease, or have no effect on the calculated acid for the second one? Yeah, I'm pulling it up right now. All right, so here's our M1V1 calculation or the factor label calculation. Now, for part C, right, using this idea, we have to think, okay, if they added too much sodium hydroxide, that would make this number bigger. If this number's bigger and we divide across, what would happen to our molarity? It would get bigger. And so that's all you have to say. Is if the student accidentally recorded that they needed more moles of sodium hydroxide means more moles of acid. More moles of acid means greater concentration. And I'm pretty sure that that's what they walk through in their explanation. So they say the error would increase the calculated acid concentration, right? A volume of sodium hydroxide larger than actual volume would reach the equivalent of the calculated moles that would be greater than the moles actually present. The assumption the moles of acid are the same. Blah, 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 blah. Okay. We got 20 more minutes. I can do a couple more. Let's see. Haley asked for 5C. So let's look at 5, and then Lauren, we should have time to do 4, so I'll go to 4. So let's go up to question 5. Let's see, 7, this is 5. Okay, let's see. Oops. That's 4, 5. So whenever I see time, my brain should audibly say rates, laws. We're going to go over rate laws in our review next week or the following week. I can't remember. Let me double check. Oh yeah, next week. So next Wednesday, we'll be going over rates. Okay, so let's see, 5. At high temperatures, betadine, the rate of the reaction was in a vessel. 2 trials using different concentrations. Data were plotted. So we have the concentration versus time. We have the natural log of the concentration versus time. We have 1 over the concentration versus time. If you look at that, your brain should automatically say, oh, look, concentration versus time, natural log of the concentration versus time, 1 over the concentration versus time. You'd say, oh, well, this one's linear. That means the reaction is second order, right? 0 order, first order, second order. And they'll almost always give you these 3 ideas to kind of get you to predict something. So for sure, this looks like a second order reaction. Now, did they actually ask that question? Let's see. It says, for trial 1, calculate the initial pressure in atmospheres in the vessel. Assume that initially all of the gas present in the vessel is that. So we have concentration. So what do they ask you to do? They give you the temperature. They give you the concentration. They give you the volume. Well, you can assume 1 liter. So you can just use P equals nRT to calculate the pressure here. So that's 1 is a P equals nRT. I think Haley asked about C, so let's do C. Okay, so B, determine the order, second order, done. C, the initial rate of the reaction in trial 1 is 0.0010 molar. Calculate the rate constant K. Okay, so if they give us the initial rate and we're trying to find the rate constant, we can remember that for a second order reaction, right, rate equals K times the concentration of A squared, right? So it's second order, so we know that the exponent here is going to be a 2. They give us the rate, we can find the concentration, and then we solve for K. So they told us the rate was 0.001, 0.0010 molarity per second. We're trying to find K. The initial concentration, if you look in the problem, the initial concentration in trial 1 was 0.02 molar. All right, 0.02 molar. Yeah, for trial 1, so it was 0.021 molar. Right, we can see that if we look at the concentration versus time graph, they just tell you it's 0.02. So you just look at the initial concentration, 0.02 for trial 1. Even though it's a second order and this one's linear, we can still use this one to look at the actual concentrations. You could plug in 100 and then invert it and get 0.02, or sorry, 50 and invert it and get 0.02, but that's fine. That's not as quick. So we can just look here, 0.02 molar is our initial concentration. So we go to the calculation, and we just plug in and solve for K. So we take 0.001 divided by 0.02 squared. and you get 2.5. So K equals 2.5, but we got to be careful about units. It needs to be 1 over molarity second. Again, we're going to go over rates and stuff on Wednesday, so we'll do a review of this. But if you have molarity squared here and you have just molarity, we can think of this as molarity to the -1, s to the -1, or we could think of it as liters per mole second in order to make those units work out. Is that what they have on the grading key? Did we do it? Let's see. Boop. So what did they do? They said from the second order rate law differentiated form, rate equals k times that squared. So plug in 0.01, plug in 0.02, you get 2.5. Done. Or from the integrated rate law, the coefficient of t is equal to 2k because of the reaction stoichiometry. Why would you? What? Yeah, don't use the integrated rate law. Don't do that. That's dumb. Don't do that. Just do this. Yeah, just do this. Don't do that. That's dumb. Yeah, that's dumb. Okay, just do this. All right. Let's go to 4A. So 4A. 4A. Phenol is a weak acid that partially dissociates in water according to the equation above. What is the pH of a 0.75 molar solution? All right, so we have a weak acid. So we're going to do an ice table, right? So let's see. Oh, we'll get to, Okay, A is good. All right, B. So B says for a certain, so you would just do an ice table, you'd plug in K, you'd find the concentration of H plus, turn it into pH, easy. Part B. So let's read the prompt on part B. They want you to circle something. It says for a certain reaction involving C6 H5OH to proceed at a significant rate, the phenol must be primarily in its deprotonated form C6H5O- aqueous. In order to ensure that the phenol is deprotonated, the reaction must be conducted in a buffered solution. On the number scale below, circle each pH for which more than 50% of the phenol molecules are in the deprotonated form, C6H5O-. Justify your answer. Okay, so you should zoom into this 50% idea. 50%. When do we have 50% of a weak acid and 50% of its conjugate base? Perfect buffer, right? And what do we know about the pH at the perfect buffer? Everyone's like, perfect buffer equals the pKa. So let's calculate the pKa. So if we calculate the pKa, they gave us the Ka. So the pKa is the negative log. So 1.1 times 10 to the negative 10th. So if we take the negative log of that, we get 9.95. So 9.95, here, let me show you my work real fast. So 9.95 is the point at which we have 50% of both the weak acid and its conjugate base. Now, if we want to have more than 50% of the conjugate base, we need the pH to be higher than 9.95, right? So we would predict that it would be, wait a minute. Sorry, lower. Let me, I read the problem wrong. 1 second. So we have a pH of 9.95. So we want to ensure that it's deprotonated. In the deprotonated form. In the deprotonated form, it's lost its hydrogen. So it's acted as a base. Okay, no, so I'm right. It is greater than. My initial thinking was right. So we want a pH greater than 9.95. So we want to circle these ones, 10, 11, 12, 13, 14. Because at these higher pHs, we've got extra conjugate base. But no, yeah, okay. Oh, man. Good thing buffers aren't actually on the AP test. Right, so remember, this is also technically a problem that would be eliminated. So we should have circled 10, 11, 12, 13, 14. Let's see what they said. Question. They said 1 point is earned for circling 10 through 14. Good. When the pH is greater than pKa, the deprotonated form will predominate. Therefore, pH 10 and above. So they did a calculation of pH equals pKa, and so then they just calculated 10 and above. So 1 point is earned for 10, 14. 1 point is for the justification. Yeah, they announced that they would eliminate buffers from the AP test for this year. Okay, we've got a couple more minutes. I can maybe do one more problem. What else we got? Detoxing the body. That sounds like someone's trying to sell you crap. The only way you get rid of toxins in your body is with a liver and kidneys. So 3 is a long problem, Lauren. We can focus. We can see how much of 3 we can get through. We can do 3A and 3B. Maybe. Let's see, Logan. So number 3. Okay, so 3 is a good experimental question. So let's zoom out a little bit here. Let's talk about 3. So 3 asks, to determine the molar mass of an unknown metal, a student needs iodine, so they react it with iodine and an excess of the metal to form water-soluble compound Mi2. So right there, we know that the metal is a positive 2, which may or may not be important, but right? So as represented by the equation above, the reaction proceeds until all the iodine is consumed. The Mi2 solution is quantitatively collected and heated to remove the water, and the product is dried and weighed to a constant mass. The experimental steps are represented below, followed by a data table. Okay, so we have our empty beaker, which weighs this much. Then we added the metal, and so if we did a subtraction here, we could find how much metal we added. We added iodine, right? Okay. We added water. The reaction occurs when we add water. Okay, so things dissolve, right? Reaction happens. Then we had our Mi2 aqueous with some leftover M. They did a filtration. So they had the Mi2, so they filtered out the leftover M. They had Mi2 left over. They heated and reheated until it got solid. Okay, so lots of stuff going on in this experiment, several steps. So they have all the data collected in this nice, lovely table for us. Okay. So given that the metal is in excess, calculate the number of moles of iodine that reacted. Okay, well, to get that, right, we need to find how much iodine we added. So if we take this number and we subtract that number, that would give us just the iodine. So 127.570 minus 126.549. That's going to give us our grams of iodine, which if we multiply by the molar mass of iodine, where are you? Iodine on my periodic table. Iodine's 126.9. So 126.9 times 2, because it's I2, grams per mole, should give us the molar mass. So let me show you my work. Right? So we're going to do the subtraction. 127.570 minus 126.549 gives me 1.021 grams divided by 126.9 times 2 gives me a very small number of moles, 0.0006340 moles of iodine. Right, very small number of moles. Okay, let's see. Is that what the grading key said for part A? Yeah. Wait, what? Yeah, apparently I plugged that in my calculator wrong. Let's try that again. Oh, oops, I didn't put the decimal. Make sure you double check your math. Oh, yep. I'm dumb. 0.004023. That number seemed really small. 0.004023. That's much better. Yeah, that's what I get for not doing my math right. I divided it, what I actually did, I divided it by 127.9 squared instead of multiplied by 2. Shame on me. So 0.004023 moles of iodine, that's part A. Part B was the one that we had a question about. So part B then asks, calculate the molar mass of the unknown metal. Okay. Calculate the molar mass of the unknown metal. So if we want to do the molar mass of the unknown metal, we have to find out how many grams are in a mole of the unknown metal, right? So let's see. Here's where my thought process is going. How many grams of metal are in 1 mole of metal? Okay. What do we know? Well, we know from the reaction that 1 mole of the metal reacted with 1 mole of iodine. We also know from part A that we used 0.004023 moles of iodine. But we used that many moles of iodine and reacted with what? Right? Let's see if we can figure out what we would put there. Well, oh, so we know how much Mi2 we formed. So we could say, we could do that. Can we do that? Yeah, let's do that. It's not quite going to get us where we want to go, but that's okay. 1.284. So that's 1.284 grams of Mi2. So what we can do is, instead of directly solving for the molar mass of the metal, we can solve for the molar mass of Mi2. Right? So let's do that. So the molar mass of Mi2 is 319.2. So we know that Mi2 equals 319.2 grams per mole. And so if we subtract out the 2 iodines, which is 253.8, that should give us just the metal. So if we subtract 253.8, that means our unknown metal is 65.4. Can't you subtract the mass of iodine from the total and get the mass of the M and then use that in the calculation? Oh, so Maggie, that's a great point. So you could also do that there. So you have to do a subtraction somewhere. So Maggie is suggesting that we take this 1.284 and we subtract out the 1.021, and that would give us grams of metal that we could plug in here. So you could do that subtraction and plug that in there, and that would work great. Or you can do what I've got and do a subtraction at the end, and that would work too. There's a bunch of different ways to get the answer here, but you should end up with 65. Naya's like, I want to go. Class is over. But yeah, just to verify, just to show you guys, it is 65.4. If you have other questions or you want more that we didn't get to questions you had, I'll be available this afternoon in Discord. Hop on, join in. I miss it too, Naya. I have posted the 2017 exam. So if you want to get going on 2017 exam, it's up and ready to go. That's going to be due next Thursday. We're going to continue our reviews on Monday and Wednesday, and then we'll go over the 2017 next Friday. Expect a new calendar for me sometime next week, but otherwise, I'll let you guys get going. So, like I do that. Yeah, if you want to take this weekend as a break, go enjoy a walk, do something like that. That's totally fine, Isaac, as long as you get done before Thursday. Have a great weekend, guys. Try to make the most. Take care of your mental health. Do something. Go on a walk. Call a friend. FaceTime somebody. Do something. Okay? That's other homework from me. Bye, guys. Have a great day.